start from where we left off. All right. I'm going to share my screen again. And all right. For Gauss law, which is the one of the important laws of electromagnetism, which relates the flux of electric field through its surface with the charge inside the closed surface. So because of that, we're going to talk about flux first. And we, in order to make it understandable, we talk about flux of water through a flat loop inside water. Suppose you have a loop and the water is flowing this way with velocity v. The flux of water, or it is called volume flow rate, means that the number of cubic meters of water passing through the loop in each second. So flux of water through the flat loop, when velocity of water is uniform and is perpendicular to the loop, can simply be written as V times A. We denote the flux by phi, and it is V times A. Remember that V is meters per second, area is meters squared, so it becomes meter cubed per second. So that's flux of water. If the loop makes an angle with the perpendicular to the velocity, in this angle phi, the flux is less, as you see, because the area that is perpendicular to the water motion is a little bit smaller with this area, which is called a perpendicular, and is a cosine of phi. And you can write, therefore, flux equal to V times a cosine phi. So it's a smaller flux. The maximum is this, but depends on the angle. But we are going to define an area vector. The area vector for this loop is perpendicular to the plane of the loop, and it has a magnitude that is given equal to the area of the loop. So this, if you write this area vector, you see that this V a cosine of phi is the magnitude of velocity times magnitude of the area vector times cosine of the angle between them. You see that the angle between the area vector and the velocity vector at this point is exactly the same as this angle phi. And therefore, this looks like it is a dot product of the area vector and the velocity vector. So we say flux of water is equal to V dot A. And for the electric field is exactly the same. Similarly, for flux of electric field E through a flat surface of area A, when E is uniform, can be written as flux of electric field equal to E dot A. And that is E times A times cosine of phi again. But this phi, it can be viewed as the angle of the area or the plane to the perpendicular to the electric field, or can be viewed as the angle of the area vector of the plane to the electric field. So we can write as E dot A the same way. So we see that when the plane is exactly perpendicular to the electric field, then the area vector, which is perpendicular to the plane, is in the same direction as the electric field, and phi is 0. And cosine of phi is 1. Then you get maximum flux through the surface. So the flux becomes E times A. And then when you have this situation, when the plane itself is parallel to the electric field, the perpendicular to the plane is perpendicular to the electric field, and phi is 90 degrees. And then you have E times A times cosine of 90 degrees, which is 0. So in this case, minimum amount of flux goes through the surface. Here, the maximum amount goes through the surface. And here, is somewhere in between. And but what if the electric field is not uniform? Here we said that the electric field is uniform and the surface is flat. What if the electric field is not uniform and the surface is not flat? In that case, we divide the surface into very small pieces so that because the electric field is usually continuous, that means that it doesn't change abruptly from one point to the other. Therefore, for each one of these small pieces, we have uniform electric field if they are small enough. Then the electric field, the flux through each one of these can be written as, just if you call it delta A, and electric field at that time becomes delta flux of electric field equal to E dot delta A, or dA. So this is the small flux going through each one of these. And of course, this E dot delta A can be positive, can be negative, can be zero, as you see in here. And if you write this in terms of magnitude, you get that. Theta is the angle between E and delta A at the location of that piece. That at any point, it's different. Note that by convention, delta A is considered to be outward from the closed surface. So here you're talking about the closed surface and the electric field, the delta A for each part of this is outward. Before that, when we talked about just a flat plane, it was not very clear about, for example, here, it wasn't clear you could take the A this way, or you could take the A the other way, because the two directions are equivalent. But here, because we have in closed surface and there's inside and outside, we can define the delta A to be outward. So delta A is outward. Therefore, the net flux going out of the closed surface is approximated by the sum of all these small contributions. So we say flux of E is almost equal to sum of all these delta phi E's, which means that for each one of these, you calculate the flux like that. There's an electric field at that point, delta A at that point, and do E dot delta A. There are some that are negative, some positive, some zero. You add all of them as numbers. So you can write E dot delta A, sum of E dot delta A. Or if you want to make it more accurate, you calculate this summation and make the delta A approach zero. Means that the smaller these areas are, the more accurate you get the result. And at the limit, you become infinitely accurate. And then that, as you know from calculus, that is called integral of E dot dA over the closed surface. But this circle that you see on the integral is because it implies that the surface is closed. All right. So integral over closed surface of E dot dA means basically this. We divide the surface into many delta A's and calculate E dot delta A at each one of those pieces and add them together, and then take the limit of such quantities when delta A goes to zero. It means the largest of delta A goes to zero. All right, and then this will be our definition, and this is what it means. So let's put that up here. This is the flux through a closed surface of electric field. Note that since dA or delta A are by definition always outward from the closed surface, then when E pierces an area element in such a way that it goes into the closed surface at that location, dA and E make an angle theta that is greater than 90 degrees. And therefore, E dot dA becomes less than zero because the cosine of theta, which is larger than 90 degrees, becomes negative. And like what you see in here, And that particular element makes a negative contribution to the net outgoing flux. So back point 1 in this figure. But then when E field is parallel to the surface of an element, theta is 90 degrees, E dot dA is 0, and the element makes no contribution to the outgoing flux, like in this point number 2. You see that the electric field at that point is parallel to the surface. So the electric field is parallel, the delta A is perpendicular, or dA is perpendicular to the surface, and the angle between them is 90 degrees. E dot dA becomes 0. And then when the electric field pierces outward, theta is less than 90 degrees, E dot dA is greater than 0, and element makes positive contribution to the net outgoing flux, like in point 3. See here. All right, so these, as I said, could be positive, negative, or 0, but then when you add them all up, it becomes a number. Either the whole thing is positive or negative or 0. Any questions so far? All right. This was an example we went through, flux through a closed surface. This is a cylindrical closed surface in a very simple electric field that's uniform. And also the electric field is along the axis of the cylinder. We can divide this cylinder into 3 different pieces. There's this cap and the other cap on the other side, and the cylindrical part. And if you look at each one of those, you see that on the cylindrical part, the round part, E is parallel to the surface, and dA everywhere is perpendicular to the surface. And then E and dA are perpendicular to each other. Therefore, E dot dA becomes 0. But in the other cases, it's not 0. So phi E can be split into 3 pieces because the 3 cases are different. So this is E dot dA on part A, which is in this case, this cap. This one is for part B, which is the cylindrical part. And this last one is on the other cap. And then you see that for part A, the dA is outward, means to the left, electric field is to the right, and the angle between them is 180 degrees. Therefore, E dot dA becomes E times dA times cosine of 180 degrees. Cosine of 180 is -1, right? And then -1 times E comes out, becomes -E integral dA. And integral dA is just the area of this part. So E times A. Let's say if A is the area of the cap. And then for the middle part, E dot dA becomes what? Becomes E times dA times cosine of 90 degrees at any point, because at any point, electric field and dA are perpendicular. Cosine of 90 is 0, so this gives you 0. In part C, E dot dA becomes E times dA times cosine of 0, because dA is outward, electric field happens to be in the same direction at that point, at all of those points. So you see that cosine 0 is 1, and E comes out, and integral of dA becomes A again, so it becomes E times A. And then if you add all these 3, you get the total flux is -EA plus 0 plus EA, which is total 0. So it is 0 because every electric field that goes into this, it comes out on the other side. And that was a good example, but then what is Gauss law? Gauss law says that this flux through any closed surface is equal to the total charge enclosed in that closed surface divided by epsilon naught. So Gauss law relates this flux to what charge is inside. This is very, very important. There are some misunderstandings about this. I want to give you some notes to make sure you pay attention to this. Remember that the area element vector dA on a Gaussian surface is always outward and from inside out. There's a specific direction for each one of those area elements, perpendicular to the surface, and that is twofold ambiguity, but we say inward and outward, can be inward, can be outward. The convention is that it is outward. That is something to remember always. And in Gauss law, the enclosed charge is the algebraic sum of all charges inside. Equal amounts of positive and negative charges inside the closed surface make a zero net flux. So there's some negative charges create negative flux, positive charges create positive flux, but then the total can be zero if there's a balance of charges inside. In Gauss law, the E field is not only due to the charges inside. The E field is due to all charges in the universe. That's very, very important. The law says that regardless of the charge distribution, form of the electric field, and the shape of the closed surface, the net flux is always proportional to the net charge inside. So that doesn't mean that these charges that are inside create this electric field. No, this electric field is from all the charges, whether they are inside or outside. But the total flux only is proportional to what is inside. All right? Like in the example that you just saw, there was some electric field that are created from charges outside, but there was no charges inside that cylinder. Another thing is that Gauss law is mathematically equivalent to Coulomb's law. However, since it is local, it doesn't involve the action at a distance. So we call it spooky action at a distance. It is consistent with theory of special relativity. So that is the importance of Gauss law. Not only it is equivalent in nature to Coulomb's law, but Coulomb's law is not consistent with the special relativity, but Gauss law is. So that's why in modern physics, Gauss law is more important than Coulomb's law. Anyhow, so here are some examples of different surfaces for. Yes. Any questions? Here, there are two charges, positive Q and negative Q, the same magnitude of charges. And there are some surfaces. We're looking at different surfaces. For example, this is S1, this is S2, and S3 is this one, and S4 is this large one. S1, if you look at S1, the electric field is outward for all points of this surface. You see the electric field is going out of this surface everywhere. Thus, the flux of the electric field through this surface is positive. And so is the net charge within the surface, as Gauss law requires. So this illustrates how it works. See, if you have a positive charge and the electric fields are going away from the positive charge, therefore, you create positive contributions everywhere. So if the total flux through the surface becomes positive. And Gauss law says it should be positive because the charge inside is positive. And if you look at surface 2, this is S2. The electric field is inward for all points on this surface. Thus, the flux of the electric field through this surface is negative. Remember, all the dAs are outward and the electric field is inward. So they make an angle more than 90 degrees, and E dot dA is negative. All the dAs created negative contribution, so the total is negative. And the charge inside is also negative. Again, the Gauss law says it should be negative because the charge is negative. For S3, there is no charges in that, and therefore Q enclosed is 0. Gauss law requires that the net flux of the electric field through this surface to be 0. That is reasonable because all the field line pass entirely through the surface, entering at the top and leaving at the bottom. You see these come here into the surface and then leave. This here into the surface and leave, right? So all these pieces at the top, they make a negative contribution to the flux. The other side create positive contribution. And because there's no charge inside, the Gauss law says that these two exactly balance each other. Of course, by the way, I have a video on YouTube that I explain in class how we get to the Gauss law. If you understand Coulomb's law, you can calculate the flux, and you see that for every case, the flux is the same as the total charge inside. And so we get basically from Coulomb's law, we get to Gauss law. It's not a concrete proof, but you can understand how it works. And but we don't usually do that because, as I said, it is not a concrete proof. This surface number 4, which is the large surface, has no net charge in it because there is positive charge here and negative charge inside. So the net charge inside is 0 because the positive and negative are the same magnitude. Gauss law requires that the net flux of the electric field through this surface to be 0. This is reasonable because there are as many field lines going out of the surface as they are going inside. See, all of these surface elements, if you consider here, they create a positive contribution to the flux, and these ones create a negative contribution. So it is understandable that the total flux is 0. All right, any questions? All right. And some results obtained from Gauss law are discussed here. Gauss law confirms the result previously obtained by Coulomb's law in cases where there is symmetry in the problem, so that the law can be used to calculate E field. For example, E field of a point charge. Suppose we don't know the Coulomb's law, we know Gauss law. We want to see how we can come up with Coulomb's law if we know Gauss law. So they say that, for example, if we have a point charge Q, we want to see what is the electric field at distance r from it. Of course, here in the figure, we consider the electric field to be radial. We don't even need to know it is radial because we can argue this way. This is the way the argument goes. Suppose we know the Gauss law. We say that, okay, we want to find the electric field at points at distance r from the point charge. And so we take a Gaussian surface, which is a sphere centered at the point charge with the radius r. So the sphere passes through that point where we want to calculate the electric field. And then we use some symmetry arguments. First of all, we say that the electric field at any point on this surface is radial. Why is that? If suppose it is not radial, it is in some direction like this. If it is not radial, then there is a component in two directions. One is radial, one is azimuthal or tangent to the sphere at this point. And this azimuthal component or tangent component breaks the symmetry because, say, what is the preference? Why there should be a component of electric field in this way, not in this way? Because the two directions are completely equivalent. So because the two directions are equivalent, there shouldn't be any tangent component. So it should be radial only. So the electric field has to be radial everywhere. Otherwise, it breaks the symmetry. And then at any point, it is radial and therefore perpendicular to this sphere. Now that we know that, also, we also understand that the electric field at any point is the same. The electric field at this point, this point, this point is all the same. Why? Because if they're not the same, it means that there's something special about this direction or that direction or that direction. There is no such a thing. So all the directions are equivalent. So from logic, we conclude that the electric field is radial and the same on any point on this surface. All right. Once we make this argument, then we can apply Gauss law to this surface, Gaussian surface. When we have a surface where we apply Gauss law to, we call it Gaussian surface. So let's apply Gauss law to this Gaussian surface. Gauss law says integral over this closed surface of E dot dA is equal to the total charge enclosed divided by epsilon naught. All right. Now we know that the electric field is the same everywhere on this sphere, and also is in radial direction, therefore perpendicular to the surface. And dA is also perpendicular to the surface. Remember, dA is at any point perpendicular to the surface, so dA is in the same direction at any point to this electric field. So E dot dA becomes E times dA times cosine of 0, which is 1. So this becomes integral of E dA over the surface equal to Q, which is total charge inside, divided by epsilon naught. And E is the same everywhere, so we can bring it outside the integral. So E becomes somebody is asking D is perpendicular because it has to go outward. No, that was the convention. Remember, dA is always perpendicular to the surface, and it is outward. All right. So E is constant everywhere, and therefore we can bring it out. So it becomes this integral. This becomes E times integral of dA equal to Q over epsilon naught. Right? And then what is integral of dA? What is the total sum of all these dA's magnitudes? Remember, dA was the magnitude of this. Yes, dA was the magnitude of the area element. If you add all of them, what do we get? We get the total area of the sphere. And the total area of the sphere is, E times 4 pi r squared, right? Equal to Q over epsilon naught. And then we can solve for E. E becomes Q over 4 pi epsilon naught r squared, or 1 over 4 pi epsilon naught is K, so K Q over r squared. So this way you see that from Gauss law, which we started here, with some symmetry arguments, we can get to this result for a point charge. All right. So summarize this in this. And then what about a field of an infinite line of charge? We already calculated the field of an infinite line of charge with uniform linear charge density. So if we have an infinite linear charge with charge density lambda, we can use Gauss law to calculate the electric field. Because everywhere we have symmetry, we can do that. First, we argue that the electric field should be only perpendicular to the line. Why is it radial and perpendicular? Because if it is not, then there's let's say if the electric field is this way, it distinguishes this direction from the other direction. but there's no such distinction. So it cannot have the electric field cannot have a component along the line, but also it cannot have a component in the azimuthal direction for the same reason, because of symmetry. So the electric field is only radial at any point. Then we want to see what is the electric field at this point. We take a Gaussian surface and we apply Gauss law. The Gaussian surface that works here is a cylinder like that. Cylinder that is coaxial with the line and with the radius r and length L. And again, because all the area elements are also perpendicular, again, dA and E are in the same direction. And on these sides, dA is this way, dA is always perpendicular to the surface, but E is radial, so E is this way, and the angle between them is 90 degrees. On this side also, dA is this way, and E is this way, so the E dot dA becomes 0. So E dot dA only has value on the cylindrical part, not on the caps. So the integral, if you apply the Gauss law for this Gaussian surface, we can say integral over the closed surface of E dot dA equals the total charge enclosed over epsilon naught. And then we see that the E dot dA becomes E times dA, because E and dA are in the same direction on the cylinder. On the cylindrical part, the other sides are 0, so it becomes E times dA. So it becomes integral of E dA equal to charge inside Q enclosed divided by epsilon naught. First of all, what is the Q enclosed inside this cylinder? If the length is L, we know that lambda is equal to Q over L, then Q enclosed becomes Q enclosed becomes L times lambda. So we can replace Q enclosed by L lambda. And E again is the same everywhere on the cylinder, comes out, and we have E times the area, which is, what is the area of the cylinder? The area of this part of the cylinder, not the caps. Can anybody tell me? And then we put that equal to L lambda over epsilon naught.
Isn't it pi r squared times L?
That is your pi r squared times L is the volume. Try again.
I don't know.
Is if you cut the cylinder from at some point and open it up, you get a rectangle, right? One side of the rectangle is the circumference of this circle. The other side is L, right? So it becomes like this. This is L, and this side becomes the circumference, which is 2 pi r. So we can write 2 pi r L, right? And as you see, L cancels out. Therefore, E becomes lambda over 2 pi epsilon naught r. Or you can write as, because 1 over 4 pi epsilon naught is K, 1 over 2 pi epsilon naught is 2K. So it becomes 2K lambda over R, as we had before. So you see, in this case, because we have symmetry, we can find the electric field of an infinite line of charge. All right. This is the way Gauss law works for these cases. You have to do some symmetry arguments and then apply. Any questions? So this is the result. For that, you see that you can get it from Gauss law. The E field of an infinite plane of charge. What is that? Suppose we have an infinite plane of charge like that, and of course, this is part of it. It has all uniform charge density, let's say positive. Uniform charge density sigma. And you want to find the electric field at some point at distance, let's say distance h from this plane. It's infinite plane. So it extends to infinity at all directions, right? So first you argue that the electric field should be perpendicular to the plane. Why? If it is not perpendicular to the plane, it has a component in this direction. What is the significance of this direction with other direction? All directions are the same, so there shouldn't be any parallel component. So the electric field should be perpendicular, right? And then we can take a Gaussian surface that is like cylinders. Oops. That like cylinder, like this, with the symmetrical on both sides. Sorry. With the same. Oh, I went too far. With the same distance h on this side too. And then you see we can apply Gauss law to this cylinder. And then for any point on the side of the cylinder, you see that the electric field is perpendicular to the plane, so it is this way. And the A is this way, perpendicular, and the contribution is 0. So every point on the sides of the cylinder, the contribution is 0, and except that points that are like this on the caps. This is the A, this is E. In this case, this is the A outward, and E is also away from the plane. So you see, this side, the cylindrical part, creates 0 contribution, and these two make a positive contribution. This positive contribution. So how much is that? So we say integral over the closed surface of E dot dA becomes equal to the total charge inside Q enclosed over epsilon naught. So, and you see that for the caps, E and dA are in the same direction. So this becomes E times dA, so it becomes integral E dA on caps. All right, equal to charge enclosed that we need to figure out. Sorry, what is the total charge enclosed in that? This part of the cylinder, say this part of the plane, is inside the cylinder, and if the area is A, we can say because sigma is Q over area, then Q inside is equal to sigma times A. So it becomes sigma times A over epsilon naught, right? And then for this side, you see that the electric field, if you are symmetrical distance, electric field is the same everywhere. It can come out, so it becomes E times 2 areas equal to sigma A over epsilon naught, right? And then A cancels out, and E becomes sigma over 2 epsilon naught. All right? Which is the result we found before. Does it make sense? Any questions? So E becomes sigma over 2 epsilon naught. And it does not depend on the distance. Right? Any questions? All right. So these are familiar results from before that we knew from Coulomb's law, but now we could find them also from Gauss law. But there are cases where Gauss law enables us to obtain results that are not easy to get from Coulomb's law. One of them is the shell theorem for spheres. The electric field of a uniformly charged spherical shell is 0 inside, and for outside, E field is the same as that of a point charge with the whole charge of the sphere at its center, as if the whole charge is collapsed into its center. So if you have a spherical shell of charge Q uniformly distributed over its surface, if you are inside, the E is 0. If you're outside, E is like you put all the charge here, Q, and calculate this the same as Coulomb's law. The electric field outside, E, oops, E is KQ over R squared, where R is this distance from the center to this point. That's very unintuitive. And it is hard to see because you see that, sorry, each one of these pieces on the surface created their own electric field, DE, and you need to add all of them. One of them is here, for example, creates electric field like that, DE for that part, and you add all of them. Why is it that the total becomes like this? You can do that in calculus. You can add all of these very carefully and come up with this formula. We didn't do that because I didn't want to use a lot of calculus in this course, even though it's calculus based. And Newton, as I said, knew this for gravity, but it took him 20 years to do that. He had to invent calculus to be able to do this. And he kept a law of gravity, which is exactly the same. You know, the gravitational acceleration becomes G m over R squared. So for example, for the Earth, if you want to calculate the gravitational acceleration on the surface of the Earth, you can put the whole mass of the Earth at the center and use the radius of the Earth here and calculate that. And in fact, if you put the numbers in, you see that it is 9.8. If you put mass of the Earth and radius of the Earth with just G constant, G is in that case 6.67 times 10 to the negative 11, instead of K here 9 times 10 to the 9. There are different value constants, but the laws are exactly the same. So I don't want to get into that in detail, but it is very, the only thing I want to mention is that it is possible to do that with calculus, but it's very, very hard. So how do we get that from Gauss law? We can use Gauss law to get that very easily. So let's say we want to find the electric field at this point. At this point, that distance R from the center. And the charge is all over the surface. And it is uniformly distributed. We take a Gaussian surface again, with a spherical Gaussian surface that is concentric to this with this sphere. Again, we make an argument that, okay, because of the symmetry, the electric field should be directly outward or inward, depending on the charge, and there should not be any component in the tangent direction. And also the electric field on this surface everywhere is the same because the distance to the center is the same. Other than that, there's no distinction between the different points. For example, the electric field here is the same as the electric field here, the same as here, the same as here, and they are all in the radial direction. All right, and then we apply Gauss law again. So integral over the closed surface. This is our Gaussian surface. So integral of E dot dA is equal to the total charge enclosed divided by epsilon naught. Again, we do the same argument. This becomes E dot dA becomes E times dA, integral E times dA without the dot product, just the magnitudes. And then E is constant everywhere. E comes out. E integral of dA equal to Q, total charge inside is Q divided by epsilon naught, and the E times 4 pi r squared. This is the radius of the Gaussian surface. This is R, right? This distance is capital R. We don't have anything to do with that. We take a integral, come 4 pi r squared, little r squared, which is Gaussian surface radius, as Q over epsilon naught, and then E becomes Q over 4 pi epsilon naught r squared, again, or KQ over r squared. So the Gauss law gives you very easily the result that says, okay, if you want the electric field of a uniform spherical shell of charge Q, just put all the charges at the center and treat it as a point charge. This is Gauss law. This is the result of Gauss law. That makes sometimes it makes life a lot easier. And of course, if you want to do inside, if you want to find the electric field inside the sphere, you take the Gaussian surface to be inside a sphere like that with radius r, and then do the same argument, except that you have 0 here, so E becomes 0. Newton could argue and get 0 inside, but it took him 20 years to get to the outside, because this argument for inside is pretty easy. You can pretty intuitively see that, but the outside is not very intuitive. You have to do the integral. All right, so this is called shell theorem for the sphere. Gauss law gives you that very easily. There's also shell theorem for long cylinders. The E field of a uniformly charged, infinitely long cylindrical shell is 0 inside, and outside the cylinder, the E field is the same as that of an infinite line of charge with the same linear charge density as the long cylinder, as if the cylindrical shell is collapsed into its axis. Again, you can do a similar argument and see that for Gauss law, it doesn't matter how the charge is distributed, as long as there's symmetry, you get the exact same result. But again, that one is very easy to get, very hard to get from Coulomb's law. And also for solid spheres, for outside a solid sphere, it acts like a point charge with all the charge at the center. But inside the solid sphere with uniform volume charge density, the E field increases linearly from 0 at the center to a maximum on the surface. Again, you see, if this is a solid sphere, it means that the charge is distributed over its volume uniformly, and you want to find the electric field here, you take a Gaussian surface, and for Gauss law, you see that it doesn't matter if the charge is at the center or it is distributed over the surface or distributed inside the surface. It's all the same. You can as long as there's symmetry, you can make the same argument and come up with E equal to KQ over R squared, where R is from the center, okay? But when you are inside, it is a bit different. And of course, that is also very, very hard to get from Coulomb's law. So how do we argue for inside? Now, suppose that there is a, well, let me magnify a little bit. This is the sphere, it's full of charge. It's volume charge density rho. And you want to see what is the electric field at the distance r that is less than capital R. This is R, less than capital R. And what is the electric field here? In order to get that, you use a Gaussian surface that is concentric with the sphere and with radius r, a spherical Gaussian surface, and then do integral E dot dA for this Gaussian surface. Now the small one is the Gaussian surface, equals to Q enclosed over epsilon naught. So again, do the same argument, you know, the electric field should be radial because of the symmetry and all that. This side gives you E times 4 pi R squared, right? The other side is Q enclosed is a little bit tricky. What is Q enclosed here? Because if the total charge of this is Q, what is Q enclosed here? Can anybody tell me what is the Q enclosed in this case? If the total charge of the sphere with radius capital R is Q and the charge is uniformly distributed over the volume, what is the charge inside the Gaussian surface? Because this Q enclosed is inside the Gaussian surface. We need to calculate that. This is not very obvious. What do you think?
Would it just be the inside of the smaller radius part?
That's right, but how much is it? In terms of R, capital R, little r, and capital Q, total charge.
It would be like R minus R, or big R minus small r.
Big R minus a small r is this distance. What does it have to
And
do? Oh,
it will be Q minus, could we do like Q minus like,
yeah, how much charge is here? You know?
yeah,
But that's also as hard as saying how much charge is not there, right? So that's a head scratcher. So remember, the charge density rho is constant, right? Rho can be written as the total charge divided by 4/3 of the volume, right? 4/3 pi R cubed, right? And this is also the same as Q enclosed over 4/3 of pi R cubed, right? Is the total charge inside the Gaussian surface divided by the volume of the Gaussian surface, the same as the total charge of the whole sphere divided by the volume of the whole sphere. And now this, it gives you the enclosed charge. If you can cancel the 4/3 pi, and then you have enclosed, Q enclosed equal to Q times R cubed over R cubed, right? So if you put that in here, say Q over epsilon naught times R cubed over R cubed. Now you see there is R squared here, R cubed here. So this R squared cancels with two of these, you get R over there. And therefore, E can be written as Q over 4 pi epsilon naught R over R cubed, capital R. Right? So, or you can write it this way, E equal to Q, 1 over 4 pi epsilon naught can be written as K also, K Q over R squared times R over R. Right? So you see that it is the electric field of the whole sphere on the surface times the fraction of the distance that you are to the surface. So the E field increases linearly from 0 at the center to a maximum on the surface. That's what this means. Okay. I'm going to talk about that again. The same you can say from long cylindrical solid. For outside, a long solid cylinder also acts like an infinite line of charge with all the charge on the axis. But inside a long solid cylinder with uniform volume charge density, the E field increases linearly from 0 on the axis to maximum on the surface. Okay, this is what I just created. You see, remember, outside, if R is greater than R, means the distance is to the center is greater than the radius of the sphere, means that you're outside. And the electric field is KQ over R squared. It's the same as all the charge collapse into the center. But inside, it is the formula I just derived. So if you look at it this way, this is the sphere with radius R, and this is the Gaussian surface that is shown in purple. And it's here, it says Gaussian surface. And the electric field is like that. You see that the electric field as a function of radius distance to the center, it goes linear like this. You see, this was exactly this equation. And because it goes with R, if R is 0, it gets 0. If R is capital R, means at this point, then becomes KQ over R squared, which is this, or 1 over 4 pi epsilon naught Q over R squared. So it goes linearly from 0 to that maximum, and you are inside. And then when you are outside, it acts like a point charge. All right, so this is, again, something that is hard to get from Coulomb's law, but you can get it from Gauss law very easily. Any questions? All right, again, the same is for cylinder. I can do the same thing, but you get the idea. For outside the cylinder, you have 2k lambda over R, means that the same as a long line of charge. But for inside, again, becomes 2k lambda over capital R, which is the electric field at the surface, times R over R. And in this case, lambda is Q over L, means the total charge of the length L of the cylinder divided by the length L, and the volume charge density becomes Q divided by pi R squared L. You see, the charge divided by volume. You have a linear charge density lambda, but we have volume charge density here. In this case, becomes the charge of length L of the cylinder divided by the volume of length L of the cylinder. And Q and L are related. Q and lambda are related, as you see. Q should be equal to lambda L, and is also from here, you see from this equation, Q is equal to lambda times L. From this equation, Q is equal to rho times pi r squared L. So these are, we can put these sides together and L cancels, and then you get lambda equal to pi r squared rho. So lambda, the linear charge density of a solid cylinder, is equal to pi r squared, the area, times its volume charge density. Okay? So these are some results by Gauss law. As you see, the Gauss law makes it very easy as long as there is symmetry in the problem. But of course, if there's no symmetry on the problem, for example, for the finite line of charge, you cannot use Gauss law because you cannot say the electric field at this point doesn't have any component. It does have a component, and that makes it hard to calculate. The electric field is kind of like this. It is not perpendicular to the line, so you cannot argue from Gauss law and get the electric field. For example, that formula that I drove for general case is not possible to get from Gauss law because the system doesn't have symmetry. But if the system has symmetry, it is easy to get from Gauss law. Some of the results that are very hard to get from Coulomb's law are this. Isolated conductor. From Gauss law, we can say that all the excess charge on an isolated conductor is located only on the outer surface of the conductor. So from Coulomb's law, you say, okay, the charges are repelling each other, so they go to the surface. But what if you keep adding charges? Keep adding charges and more and more and more. So say that, okay, there's so much charge on the surface, some of them bound to go under the surface. It is not very easy to understand why none of them go under the surface. But from Gauss law, we can see if you have charges on this conductor, we know that by the definition of conductor, the electric field is 0 inside the conductor. So we can take a Gaussian surface inside, as you see here, or here in this case. You get a Gaussian surface inside, and you write integral for this Gaussian surface, E dot dA equal to Q inside enclosed over epsilon naught. But the electric field is inside, so all of this E dot dA becomes 0. So this is 0 equal to Q enclosed over epsilon naught. Therefore, Q enclosed is equal to 0. Means that there's no charge inside this Gaussian surface. And then you can do the same argument and make this Gaussian surface larger and larger to approach from within, to approach the surface of the conductor. All this argument holds as long as this surface, Gaussian surface, is within the surface of the conductor, and you can approach it to the surface. You see that all the excess charge has to go only on the surface, no matter how much it is, no matter how enormous the charges, extra charges are, they are all on the surface. So that comes from Gauss law. That's not easy to get from Coulomb's law. Another thing is that if you have a cavity inside the conductor and there's no charge inside the cavity, then you make the same argument, say all the excess charges go only on the outer surface of the conductor. All right? But if you have some charges inside the cavity, like it is suspended somehow, if you have charge Q suspended here, if you use this Gaussian surface that's purple in here, again, integral of E dot dA So E dot dA is 0 for this surface. 0. Therefore, the total charge enclosed is 0. But because there is a charge Q here, negative Q should be on the surface. Negative Q should be on the surface. Because you can now make this Gaussian surface smaller and smaller, and approach it to the surface of the cavity now. And then you see that for all of those Gaussian surfaces on the way, you can make the same argument. There's no net charge inside. Therefore, if there is a positive charge in the cavity, there should be a negative charge, the same magnitude, on the surface of the cavity, right? And of course, if the whole conductor has a total charge QC, or Q of the cavity, then there's negative Q on the surface, inner surface. Those should be QC plus Q on the outer surface. All right? Or if the conductor, the yellow conductor is now neutral total, but then if there is negative charge Q on the inner surface, there should be positive charge Q on the outer surface. All right? But this is very important for some of the problems that we're going to see later on. All right, any questions? All right, another thing is that the E field at the surface of a charged conductor. Now, suppose there's a conductor like this. There's a charge on the surface, and because these charges create an electric field. We want to see what is that electric field, how much electric field is there. First, we argue that the electric field should be perpendicular to the surface. Why is it perpendicular to the surface? Because if the electric field is not perpendicular, it has a component parallel to the surface, and that makes the charges move. And then the charges adjust themselves until there's no parallel component. So in equilibrium, the electric field on the surface of a conductor is perpendicular to the surface of the conductor. But how much is that? So in order to, let's say this is a surface of a conductor with charge density sigma, we can make a small like this from inside the surface. You see, this is the surface. We make a small cylindrical, like a cylindrical can, and the caps of the can are parallel to the surface, and it's very, very, very small. And the sides of the can are perpendicular to the surface. So the electric field is perpendicular, so it goes out of this cap and it goes right, it skims over the surface. Inside the conductor, there's no electric field. So if you do integral of E dot dA for this whole thing, there's no contribution for the can, part of the can that is inside, and there's no contribution of the sides of the can. The only contribution is here where the dA is in the same direction as E. So this becomes Q enclosed over epsilon naught. And E dot dA for the whole surface becomes just E at that point times the area, because area is small enough so that the electric field doesn't change from one point to the other. So it becomes E times A equal to the charge inside. What is charge inside? Again, you know, sigma is Q over area, means charge per unit area. So Q is equal to sigma times the area inside this can. So it becomes sigma A over epsilon naught. And A cancels out, the E field becomes sigma over epsilon naught. All right, so it's twice the electric field of the same infinite plane of charge with the sigma. See? So here is the better shape of Gaussian surface. Yeah, we have E perpendicular to the surface, and E goes out of this top cap. And you can say the total contribution here is E times A here, the total, because on the sides here, on the sides that are outside, the electric field is perpendicular to dAs. And if you consider a dA, you see, dA is like that. But on the surface here, dA is in the same direction as electric field. And then, the argument goes the same way. E times A becomes total charge in here. The total charge in here is sigma times the area. So we get this result. All right, so we get E times A, the total flux, equal to sigma A, total charge divided by epsilon naught, and then A cancels out. E becomes sigma over epsilon naught. All right. E field between oppositely charged parallel plates. So if you have two parallel plates that are, one is positively charged, one is negatively charged, the same magnitude of the charge, and if the planes are very, very close to each other, you can idealize it and say that the electric field is like, for each one of these, is like an infinite plane, which is the case, for example, for the inside the capacitors that we're going to talk about later. Capacitors, the distance here, d, is much, much smaller than the dimensions of the plates. So each one of, if you look at this point, the plane look like an infinite plane. So each one of these creates electric fields, and you can see that these two infinite planes here, E1 is sigma over 2 epsilon naught, E2 is sigma over 2 epsilon naught. So they cancel each other. Inside, they add to each other, become sigma over epsilon naught. Outside, this side, still E becomes 0 here, E becomes 0 here. Inside, E becomes sigma over epsilon naught. And if you apply Gauss law to this S1, to this surface S1, you get the same thing. See the sigma of the plates, the charge per unit area of the plates, divided by epsilon naught. As we said, because it's a conductor, you can take the cylindrical Gaussian surface and gives you exact same results. So in this case, also E equals sigma over epsilon naught inside and 0 outside. All right. And especially this happens because, as we said, for infinite plane of charge, the electric field does not depend on the distance. It doesn't matter whether this plate is here and this one is farther away, they create the same exact electric field. All right. So this is basically all the material in this chapter. So I'm going to stop here, and then because we are out of time as well, and then we're going to do some more example problems next time. Any questions?
Professor, will you be posting these notes
Yes, I will.
today? Oh, okay, thank you.
Mhm.